Hey, AP Stats kids, today we're looking at 6.3b. We're going to deal more with binomial probabilities. We'll be looking at normal distributions and binomial probabilities, and we'll also be looking at finding the mean and standard deviation the easy way. So let's start off almost with a quick review from last time. Let's go and read this. You guys can read it. It's draw 3, get 1 free promotion. Okay? And then they get to touch it, and then they can win a free lunch. And if the chosen card is a 3, their order's free. Otherwise, they have to pay the bill. So it should be a third, right? Not a third, it's going to be less than that. But on the first day of promotion, 250 customers put their lunch orders. What's the probability less than 10 of them win a lunch? Alright, let's do it. So what we're going to be finding... By the way, I don't own this. I don't own this. My computer's looking crazy. So we're going to denote Y. Y. That's the number of customers who win a free lunch. So N is going to be 250. Now the probability, okay, draw 3 given free. You're drawing 1 card from a standard deck. It needs to be a 3. Is 4 out of 52. There's 4 3s, right? 52 cards. So find the probability that that's less than 10. Alright? Alright. Alright. I don't know why that less than 4 is there. Alright. So we're going to go right to the calculator. Binomial CDF. And, gee golly. NPX, right? For this example, there's 250 trials. That's my probability. Looking for 9, and we're doing CDF because that will give us 0 through 9, right? That's less than 10. When I plug in my calculator, I got 0.00613. All right, don't forget this is in distributions. We're doing CDF because we're finding all of them, not just one specific value. All right. All right. So now. Same thing, draw a card, press a button, win a free lunch. So, you find out only 9 customers actually win a free lunch that first day out of the 950. Should we think the computer program's actually working? Well, remember the 5% rule. 0.006 is way less than 5%. So, because the 0.06 is so low, when it's fewer than 10 customers, that tells me I don't think the program's working correctly. We have convincing evidence that the computer system's flawed because getting a result of 9, if it was accurate, is very rare. Okay? It's less than 1%. Okay? Because it's less than 5%, it's convincing argument that it's not a 4 out of 52 shot. Okay? It's no bueno. Now let's look at the probability distribution. We're looking at blood types again. Type O blood type. Where X is the number of children with type O blood point. Type O blood type, considering we had 5 kids. It's a lot of children. Okay? So I graph it. It looks like that. We want to describe it. Or let's look at it. So we have a peak at 1, and it's slightly skewed to the right. We've done this before. I'm going to go very fast through these. Alright? And then I go slow. Hi-ya. Let's do 1. Let's change the numbers. Let's change N is 5 and P is 0.51. And 1 is 0.8. You see, as P changes, it changes our shape. If P is close to 50%, you're going to have a symmetric graph. If P is greater than 50%, it'll be slightly skewed to the left because there'll be a few on the left side that can pull it that way a little bit. All right? We good? All right. Meat and potatoes. What if we want to find the mean of a binomial distribution? This formula is actually a lot easier than the ones we've been doing. All right? So the mean, the expected value, given a lot of trials, what we'd expect to get as an average is n times p, where n is your trials, number of trials, and p is the probability of success, right? Not too bad. Let's see one. Oh, my neck. Oh, let's not see one yet. Just kidding, y'all. This one's a little bit tougher. These formulas are given to you on the AP test. This one's n, p, 1 minus p, square root of it for standard deviation. So it's your number of trials times your probability of success times your probability of failure. Okay? Gosh, there's something in my eye. It's probably math knowledge. Let's just do this. It's a formula. We're going to plug it in. Remember, these formulas only work for binomials. We'll get different ones for geometric and such. Please pause this and read this. But there's 21 students in the AP course. There's a third chance that each kid gets the cup correct of the bottled water. So X is the number of students who got correct. At the right is the histogram of it. Let's calculate and interpret the mean. Well, the mean of X is going to be equal to n times p, right? N is my number of trials. So for this one, there's 21 students going to do it. P is my probability. They have a third shot of getting it right. So my mean is going to be 7. So that means given many trials of size 21, I would expect, or the average number of students to get it right will be 7. Let's see what they got. Ta-da! If all students in Ms. Hograth's class were just guessing and repeat this activity many times, the average number of students who correctly guessed would be 7. We can't say for one trial because sampling variability. You have to have the many. Alright. Same question, different question. What about the standard deviation? So this is square root of n, p, 1 minus p, right? So our number of trials, there's still 21 kids in this room. It's still a third chance of success. Now what's the chance of failure? Well, what's 1 minus 1/3? It's 2/3. Alright. That'd be what, 7? 14/3? 14/3. Let's see if I can do this in my head, because this is riveting television. 4.6 repeating? Let's see if I was right. That's what I said. 2.16 repeating. 14 divided 9. 9 by 9. Alright, so cool. So, if all students in Miss Hogwarts class were just guessing and repeated the activity many times, the number of students who guessed correctly would typically vary by about 2.16 from the mean of 7. Okay? Cool. Now, in real life, when you do a poll, when you do an activity, you're going to be doing this without replacement. Now, many of you might be saying, but if there's not replacement, then it's dependent because the probability changes each time. So how do we get around that? Well, if we have a large population and we're taking a small sample from it, that tells me that, like, if I have 1 million people and I pull 10 people from it, that one person's response might take a person out of the pool, but it's such a huge pool that it won't affect the probability very much. Like, let's say we're pulling 1 million people, or we're seeing people's hair color, and the first person has a 4 out of a million chance of having that, or that's a bad example, like a 400,000 out of a million shot having that hair color. Then the next would have a 399,999 out of 999,999. It doesn't change that much. Okay? So it's approximately binomial still. How do you check? Right here. If the sample size you're taking is less, if the sample size you're taking is less than 10% of the population, then it can still be binomial. You're not affecting enough. Okay? So, if your sample size, that's what this means, if your sample size, n, is less than 10% of the population, then it passes the 10% condition, okay? So it's still, it wouldn't be independent, but it'd be pretty darn, it would be approximately independent, like me. So let's look at it. So we'll have 500 teenagers between 14 to 18, and we're going to ask them questions. 12% of the teens have debit cards. And we use X to be the number of teens in a random sample, size 500, who have a debit card. Okay? Why can we use this as binomial even though it's without replacement? Well, that's easy. 500 is less than 10% of all the teenagers. So removing one doesn't change the pot that much. And to do the normal stuff, to be normal, I would do binom CDF, 500 trials. P is 0.12 because that's our probability of success. And X would be 50 because we're looking for 50 or fewer. And we're using CDF, so we're adding them all up below it. Okay? Binomial CDF. This next part is not required for the AP test, but I make you know it because it's nice to know. This says as n gets bigger, the larger your sample size, the closer you get to being normally distributed. Because there's less variability. The bigger your sample size, the less variability, the closer you are to a binomial distribution. Okay? Now, we can use the law of large counts to see if something is going to be close to binomial based on the law of large count says stuff. No, it says that, one second, I'm using my mouse. If n times p is greater than 1 and n times 1 minus p is greater than 10, then we pass law of large counts and we'll be approximately normal. Alright? So we can use normality if our law of large counts works. Okay? So if our number of trials times probability, if our expected value is bigger than 10, if our mean's bigger than 10, and our mean of failures, n times 1 minus p, is bigger than 10, we pass the law of large counts, which means our binomial is approximately normal. Bell-shaped. Okay? You can read that. It's been a long day. Still doing math. Alright. Same question we had before. Why would this show approximate normal? Okay. Well, our number of trials was 500, right? 500 teenagers. Probability of success is 12. So 500 times 0.12 is 60, which is bigger than 10. And our failure rate, 500 times 0.88, is 440, which is also bigger than 10. So it can be normal. It's normal. So if we would have done normal distribution instead of binom binomial. I would just use binomial, but whatever. Watch this. We get like the same answer. Upper, lower, mean, standard deviation. I'm not too worried about that. Don't worry about that part. Just know the law of large counts. And that's where we'll end it. Have a great day.